So at this point, I'd like to introduce the next speaker, and that's Dr. Peter Dusicka, who is an associate professor in our department of civil and environmental engineering. His teaching and research interests, of course, are effects of earthquakes on buildings and bridges and infrastructure. He also manages the infrastructure testing and applied research. Team of students and faculty are involved in earthquake research in that lab. One of his recent projects had to do with ODOT and OTREC, sponsored research on basically on vulnerability of bridges in the state of Oregon. So we are mighty pleased that has taken place, and he's going to get a chance to talk to you tonight about that. He's also been on various reconnaissance teams investigating post-earthquake damages in different countries. So without any further ado, Peter Dusicka.
Good evening, everybody. Thanks very much for spending the Friday night with us. Okay, so I'm going back to the question of are we ready for an earthquake? And my topic is going to be revolving around our bridges. Before I get going, I just want to make clear that even though I'm going to present some results of research that has been sponsored by various people, clearly whatever I say is completely my opinion, and I do tend to be opinionated. So don't hold them responsible, hold me responsible. And I also have a series of graduate students and undergraduate students behind me who essentially did most of the work anyway. All right, so I think in order for us to understand seismic vulnerability of bridges, we first need to understand the importance of bridges. So I'm putting up a slide of an example of the role that bridges play in our transportation system. This particular example is from 4 years ago-ish, when there was it wasn't a bridge that was down, but it was a short piece of a highway, I-5, just north of here, that was down due to a flood. Just to give you a sense of the lack of redundancy in our transportation network, the closest detour for moving goods up and down north to south between us and Seattle was about 300 to 400 mile detour, which was estimated to cause orders of magnitude about $4 million a day just for the truckers. So if you imagine the bridges being points along a transportation network, then you quickly realize that if any one of those points go down, then depending on the redundancy of the network, you may or may not, and in the case of Pacific Northwest, you typically do, cause damage not only to the bridge itself, but also to the society as a whole. And clearly, bridges are important for immediate emergency response, as well as goods and services well after the event. So now, hopefully, that we understand the importance of bridges, we can talk about the vulnerabilities. And you heard Scott talk about our sort of gradual gain in knowledge in terms of the risk, right? So if we take the risk and we sort of understand the fact that we've learned a lot over the last few decades, then what I'm going to talk about is, well, even if we knew what the risk was, us as engineers and us as bridge engineers haven't really quite understood how to design for these things anyway. So even if we did know, I think we probably would have been at pretty much the same place. So if you start thinking about how we came about our current level of knowledge in terms of bridge earthquake engineering, it really was triggered, at least in the U.S., by the 1971 San Fernando earthquake. And most of you know California is the one that's been getting most of the earthquake attention in terms of having earthquakes in areas that are populated. But San Fernando was really a wake-up call, where a lot of the bridges have gotten damaged in California, and has really drawn a few lessons for Caltrans, in that they essentially looked at the way that they design bridges, and all of a sudden there were a few lessons that they learned from it, and the seismic design has essentially steadily progressed from then on. So some of the lessons that were learned was Bridges are typically, or have been, designed for temperature expansion, right? They're fairly long structures. They're out in the elements, so they expand and contract, so you have these expansion joints in the bridges. Well, that earthquake really showed that if you can minimize the number of expansion joints in a bridge, the better off you are. They also learned that taller columns do better than shorter columns. They also learned things like you end up putting steel into concrete to help it along. The amount of steel and the position of that steel is actually really quite important. So from then on, we sort of move on to other types of earthquakes, and being engineers, we're kind of reactionary, right? So we essentially learn pretty much from every event. But we go back to California in 1989, we had the Loma Prieta, and there we also had quite a bit of damage. And we learned a lot about column integrity. Bridges tend to be non-redundant structures. That means that they have a few elements that resist things, unlike buildings that often have multiple load paths. So the column of a bridge tends to be quite important, and knowing how to design that well really hasn't caught on until about the 90s. Right? So it took Caltrans about 10 years, from 1971, another 10 years after that, to start instituting a retrofit program. So it wasn't really until the 1990s that they started retrofitting, but they've certainly learned a lot of lessons from their earthquakes. They also learned quite a bit about signature bridges. So major bridges tend to have, there are few and far in between, so if one of them goes down, you have a major impact. So in this case, the San Francisco-Oakland Bay Bridge, which carries on the order of 250,000 cars a day, if that's down, that obviously causes a little bit of a headache to the city. And then as earthquakes continue to hit us, we as engineers who build stuff in the way of the earthquake have started to learn things. And one of the things was, well, if we do have expansion joints in bridges, well, maybe we should make sure that they're long enough, because if the bridge happens to slide off that expansion joint, then results like this happen. We also learned things about torsional response, which is if you have an irregular structure, and even if you hit it with an earthquake in just one direction, that structure responds in a different direction, just due to its own geometry. So we learned that in Northwich, for example, where you have skew in bridges, which is where the bridge runs at an angle to whatever it's crossing. We also learned through an earthquake in Japan that strength is not enough. It's not enough to build strong things when we talk about earthquakes. And in fact, we now know that ductility is a lot more important, essentially the ability to absorb energy, not just to stand there and withstand it. And the Japanese didn't really learn that until essentially the Kobe earthquake in 1996. So what you see there is a fairly strong column, but all you need is 0.001 larger demand, and it's not strong enough anymore. And we continue to learn these lessons, and unfortunately that just keeps going. So the importance of, again, strength is not enough. The importance of understanding the structural behavior then becomes quite important. So the example you see there is, again, actually that one's from Taiwan, from the Chichi earthquake. The bridge on the left is what it used to be. Again, it was built more for strength than ductility, and the bridge on the right is the replacement for it. So it may not look as intimidating, but it sure will act better in an earthquake, for example. We also learned a lot about simply supported spans, i.e. having bridges that go from one support to the other, as opposed to having a bridge that's continuous over a lot of supports. And it turns out that simply supported spans, especially if they don't have enough seat to sit on, don't particularly like being moved back and forth. And there's an example from an earthquake, from a recent earthquake in Chile, and we've seen that starting from 1964 in Alaska to essentially now. Closer to home, this is the Nisqually earthquake example. You don't need to have a collapse to cause a lot of damage. So we didn't actually have a bridge collapse in Washington, but there was a tremendous amount of damage. And this may not be common knowledge to non-engineers, but we don't build bridges, for example, to survive the earthquake and be functional. So we achieve our design goal if we don't kill people. So even modern bridges are built to essentially not kill people, but that doesn't necessarily mean that you can use them afterwards. Another problem is that even if we knew how to build the structures, in this case the bridges, well above ground, it's also important to know what's below ground. And Scott mentioned liquefaction as a major problem, and as part of liquefaction you get lateral spreading. So essentially, if you have a bridge and one side of the bridge decides to go closer to the river and the other side of the bridge doesn't want to go in the same direction, then you sort of have a problem like you have here. This is the pedestrian bridge in New Zealand following the Christchurch earthquake that used to be straight and didn't have any hills. So how does that relate to us here? So essentially what that conveys is a picture of, we really kind of learned a lot about bridge behavior, so leaving the risk aside. So let's look at what that means to Oregon. So if you look at the bridge inventory in Oregon, which is that graph over there, where on the x-axis you essentially have the date at which a bridge was completed and the number of bridges that were built, you sort of get a sense that majority of our infrastructure, bridge-wise, was built in the 60s, 70s, and 80s. Okay? And if you think back about what I just said about what we know about structural behavior of bridges, well, we didn't really know a heck of a lot in terms of how to design properly quite yet. So the little writing on top essentially tries to indicate how much we knew and what we designed for in terms of earthquakes. So it wasn't really until the 1990s that ODOT has adopted fairly rigorous seismic design codes for bridges. So that leaves that whole inventory on the left-hand side that's a little bit shaded of bridges that we own. You own them, I own them. They're there, they're being used, but unfortunately they were built before we knew much, before we knew before we knew what we know today with regard to designing effectively to resist earthquakes. So now we have them. Well, what does that mean? That means that if you look at the value that's invested into this infrastructure, so the state of Oregon has order of magnitude or maybe 7,000 bridges or so. And if you look at how they get divided between state-owned, county-owned, city, and miscellaneous, that's that first pie chart there. So the number of bridges, about half of them are owned by county-type owners. But if you look at the value of the bridge, then it turns out that majority are actually ODOT-owned. So we're looking at about a $35 billion investment that's sitting there. If we decided to scrap all these bridges and build them again, we would need about $35 billion change to do it. So that's probably not going to happen. We know that these bridges are vulnerable because all the things that I showed you are present in a lot of these bridges. So what about we go and retrofit every bridge that we think is vulnerable? So if you take about 10 and 20% of that value, which is the cost of a retrofit, you're still at a fairly high number. So what are the vulnerabilities of bridges built in Oregon? And California ways of building things is actually very different to Oregon. So our bridges are quite different and have their own vulnerabilities and have their own little idiosyncrasies. So our typical sort of a bridge looks something like this, right? This is a fairly standard highway overpass. It has a multi-column supports. Those columns tend to be square and fairly slender. Not at all what California builds. California builds round columns that are 6-8 foot diameter type businesses, and the behavior, you may think, square, round, what's the big deal, but it actually has a fairly large impact about how you go about retrofitting these things. We have a lot of inadequate bearings. This is an example. This is just on the other side of Hawthorne. So if we have 4 inches for this bridge to be sitting on and be supported and the earthquake comes in, it's not unheard of for it to move 6+ inches. So you kind of need to be supported for another 2 inches up in the air, which probably isn't going to happen. So that's inadequate seat length again. So where are we within Oregon in terms of status for retrofit? So unlike California, who actually learned from their events, they instituted a retrofit program. We, as a state, don't have one. So there's no current funding for retrofit program in ODOT. The bridge section has been doing an incredible job with the nothing they've got, and they have been able to retrofit about 170 or so bridges of about 2,600 that they own, so a very small percentage. They've divided the retrofit into phase 1 and phase 2. Phase 1 essentially is, let's keep the structure attached, right? So if there is an expansion joint, let's put restrainers on. I'll show you an example of those. Phase 2 is, let's actually worry about things like the column not breaking, or let's do something about this liquefaction potential that we have. And that graph is supposed to show the cost involved with the various retrofits. So there aren't actually any phase 2 retrofits in the state, which gives you a sense of, hopefully a sense of urgency. There are some notable exceptions. So this is the Abernathy Bridge in Oregon City. That one's actually base isolated, essentially a method in which you help the structure by isolating it from the ground intentionally. There is the Markham Bridge that has undergone a phase 1 retrofit. And that's if you go for a walk around the river, have a look up at the bridge, and you'll see a whole bunch of cables. Essentially, the role of those cables are to hold the thing together when it starts shaking, so it doesn't fall down. So since we know about these vulnerabilities, let's try to quantify some of them. So we've done a little bit of research on looking at the vulnerability of the state inventory with regard to bridges. So we constructed some computer models. Made some major assumptions and ran some scenarios. An example of a scenario is this magnitude 9 that Scott mentioned, which essentially is a rip up and down the coast. And we made some assumptions about the bridge inventory and came up with, orders of magnitude. Oh, there's going to be about $1 billion worth of damage. That's direct, i.e., just to the infrastructure itself, and some, 170 or so million dollars loss due to traffic disruption. So this model actually took into account the rerouting of traffic due to bridges being down. We ran another scenario where we have a smaller magnitude earthquake. It just happens to build it closer to a populated area. This would be the Portland Hills Fault. So a lot more concentrated, but just happens to be in the wrong place. So again, we're up in the $1.5 billion type of damage just from the bridges alone. And that's not accounting for major crossings, right? So how about the interstate bridge? Yeah, that will probably get damaged. That actually wasn't part of the study. How about the Willamette crossings? The Markham Bridge, built 1966, did get a phase 1 retrofit in 1995, so that might actually be doing better than others. The Fremont Bridge, 1973, a good year, by the way, built might have issues. Again, those bridges are kind of beasts of their own, and they require actually detailed study to know exactly what would happen. But we certainly can take a wild guess at what could happen just based on the type of construction, the way that they've detailed it. How about the signature bridges up and down 101? Now these happen to be a lot closer to where the earthquake is, where the big earthquake, that 9.0 subduction, is going to be. And they were built in the 30s, 40s, right? So they're very beautiful bridges, but certainly vulnerable. And so we're addressing some of these unknowns with our research at Portland State University. Some of the questions that we want to answer that we don't quite have answers for yet is, so we've got this subduction zone earthquake. Scott told you that it's going to last probably more than a minute. Okay, whereas most of the stuff that we design for these days are based on California-based experience. The earthquake there lasts, maybe 20, if you're lucky, 30 seconds, of which maybe 10 seconds is actually strong motion. So what does that mean in terms of response of some of these vulnerable bridges? So that's some of the questions we're trying to answer at Portland State. What is an effective retrofit for bridges that are built in Oregon as opposed to this California type construction? And what is an impact of retrofit on our mobility? So next big earthquake, are we ready? Well, I'm here to pose more questions than answers, hopefully. But it really depends on what we're ready to endure. Will there be disruption to mobility? I think so. Will there be damage to bridges? Absolutely. Will some bridges collapse? Yeah, I think so. So to what extent are you willing to live with this? It depends. So hopefully that gives you an overview of of the vulnerability state of bridges. Like I said, unfortunately, there's no retrofit program in place, but we certainly have a lot of investment in our infrastructure that that we should preserve. So, am I supposed to introduce the next speaker? So, thank you.